Okay, let's take a look at a few more examples with the ratio and the root test. So just as a reminder, I projected the ratio and the root test on the screen, and we're going to jump right into a couple examples. So we'll just decide if we want to use the ratio or the root test, where we take a ratio of the terms or we take the root of the absolute value of the terms. And when we take the ratio, it's also the absolute value. And if the limit as k goes to infinity of that ratio or that root is less than 1, we'll have absolute convergence. And if it's greater than 1, then we'll have divergence. If we are equal to 1, well, then we've got to do something else because the ratio and the root test is inconclusive. All right, so let's take a look at this first one. Let's go ahead. I see a factorial. Factorials lend themselves really nicely to, when I see that factorial, my thought bubble, they lend themselves really nicely to a ratio test. So that's the first thing. And as we're wrapping up all of the tests for convergence and divergence, we are going to start talking about how do we decide which test to apply. So ratio tests can lend itself nicely to proving convergence or divergence when we have factorials. Now I can't say always, but it can be a useful tool with factorials. So let's jump into taking the n plus 1 term times 1 over the a sub nth term. So remember, I'm just splitting up that ratio, and I write it like that because often when we look at sequences, we have a fraction, and so then we can work with the fraction. So we'll take the n plus 1 term, we'll plug in n plus 1, n plus 1 squared. In the bottom, we're going to get 2 times n plus 1 minus 1 factorial. I'll write out all the steps. And then 1 over the a sub nth term. But the a sub nth term is given there, so it's just the reciprocal of the way the terms are defined. Okay, so let's see how does this play out. So I'm going to go ahead. I like to group my factorials together and my other terms together. So let's see. So we end up with 2n minus 1 factorial. And on the bottom, because when we expand this here, we get 2n plus 2 minus 1. The bottom here is going to be 2n plus 1 factorial. And over here, we've got n squared plus 2n plus 1, all divided by n squared. So we'll expand that out at the same time. Now, the thing with factorials, and I'm going to write this one out and then we'll talk about the relationship with the factorials. The thing with factorials is they represent however many factors are given. So in the numerator, we've got 2n minus 1 factors that start at 2n minus 1 and descend by 1 each factor until we get down to 3 times 2 times 1. Now, same thing in the bottom, but in the bottom, we're starting at 2n plus 1 and descending by 1 for each factor. So 2n plus 1, 2n, 2n minus 1, 2n minus 2, so forth, down to 3, 2, 1. So notice what happens there, and then of course we'll carry the other factor down there, n squared plus 2n plus 1 all over n squared. Now we're taking the absolute value of that, but those terms are actually always positive. So for n greater than or equal to 2, which our series started at 2. So those factors are always positive. So we could even drop the absolute value. I don't know if the absolute value or the brackets are better there, but we don't need the absolute value because these expressions and terms and factors all here are positive. So anyway, back to the factorials. So in the factorials here, notice that we're going to get a ton of canceling because in this denominator, the 2n plus 1 factorial, we end up with 2 extra terms and then everything else cancels because another way to write this, if we had left it as 2n minus 1 factorial, the bottom is going to be 2n plus 1 and 2n times 2n minus 1 factorial because there was a difference in those two factorials of 2 factors because the difference between 2n plus 1 and 2n minus 1 is 2. Therefore, there are 2 factors additional in the larger of the factorial. So, however you want to write it out, if it helps you to write it all the way out and see all the canceling, or if you can recognize, like we did here with the factorials, you can write it that way too. Oh, I just caught on here that this n should actually be n squared. I see that from above. So that should have been n squared. So let's get that in there. And now let's carry down what we've got left after all of our canceling. So we've got the limit as n is going to infinity. In the numerator from the factorials, we just have 1. In the denominator, 2n plus 1 times 2n. Let's go ahead and expand that out. So that becomes 4n squared plus 2n in the denominator there. Now we're multiplying by, we have a couple of choices here. We could multiply out, let's go ahead and multiply out the numerators, and then that's going to be the denominators. The numerator is just 1 times, let's pull that all in the top, n squared plus 2n plus 1. However we want to simplify this limit so we can take it. Limit as n is approaching infinity, we got n squared plus 2n plus 1 in the denominator, 4n to the 4th plus 2n squared. Okay, so now we're going to take the limit as n is going to infinity. We could look at the powers, the ratio of the powers here, and see that this guy is bottom heavy. I don't care how you want to do this, how you want to show this limit, but we need to take that limit one method or the other, or even L'Hopital's rule if we really wanted to. I'm going to look at that highest power in the denominator, the n to the 4th, and then this becomes the limit as n is approaching infinity. In the numerator, I get 1 over n squared plus 2 over n cubed plus 1 over n to the 4th. In the denominator, 4 plus, 2 over n squared. And of course, all of these, as n grows without bound, all of these 2 over n to a power are going to approach 0, and this becomes 0 over 4, or 0, which is less than 1. Remember, we're doing the ratio test here. Less than 1 means that we get convergence, not just convergence, but absolute convergence through the ratio test. So therefore, let's come back to our series and let's make a statement. Therefore, just see what the original series was. Therefore, the series of n squared over 2n minus 1 factorial converges absolutely. Remember, we always want to classify absolute or conditional convergence. It converges absolutely by, and in this case we applied the ratio test. We use RT for both ratio and root, but it was the ratio test, and it converges absolutely, the strongest type of convergence. So we've got our ratio test there. All right, let's take a look at another one. All right, let's look at this guy. I got it zoomed way out there. Let's get in there. So we've got we've got k and 3 both being raised to powers that have k in them. So I think, on this one, I'm thinking of root test. We might want to try ratio test too, but I see the root test is maybe a good possibility here, and it's good to try something different. We just showed the ratio test. So let's let L be equal to the limit as k is approaching infinity. Now, when we take the root test, we take, the kth root of a sub k. Well, that's the same as raising the absolute value of the terms to the 1 over k. So that's how I'm going to do it, because that's going to be easier in our case since we've got that powers on k, and we're going to raise that to the 1 over k. So I'm going to go ahead and apply that 1 over k to each, the numerator and the denominator, each of the terms. So we've got k to the k times 1 over k, so that's going to become just the limit of k to the first power. In the denominator, we get 3 to the 1 plus 2 to the k, and we're raising that to the 1 over k. Now remember, when you raise a power to a power, you multiply. So we're going to multiply throughout, so we get 3 to the 1 over k plus 2. And then we take the limit as k approaches infinity. In the numerator, as k is approaching infinity, of course k itself is growing without bound. And in the denominator, this little piece 1 over k is going to approach 0, and we're going to get 3 squared. So we get infinity over 9, which of course is infinite. It is growing without bound, which is greater than 1. So remember, what that tells us with the ratio or the root test is that we have divergence. So this diverges by. Therefore, the series that we're looking at, k equals 1 to infinity of k to the k over 3 to the 1 plus 2k diverges by, and in this case we were using a root test. Root and ratio tests are very similar. It's just whether you take a root or you take the ratio of terms. Okay? And this guy diverges by the root test. All right, let's finish this off with one more. Now this guy also has powers of k, but it has k to the first right here. And I know if I get k to the 1 over k, I'm going to get an infinity to the 0 as I go to, as I let k grow without bound. And because that's indeterminate, I'm thinking, you know what, let's try instead the ratio test here and see how that pans out. So let's try the ratio test because I have that k raised just to the first power, not to the kth power like we did on the last one. So again, we've been doing these now for a few different examples. So let's jump in right into it. So we're going to take the k plus 1 term, so 7 to the k plus 1 in the denominator, k plus 1 times negative 3 to the 2 times k plus 1 plus 1, and then times the reciprocal of the kth term, so k times negative 3 to the 2k plus 1 all over 7 to the k. We're taking the absolute value right there. I'm going to go ahead and sort of group in ratios. I'm going to group the like factors, like the 7k's, the k, and the k plus 1, and the negative 3. So we'll group those up. Before I do that real quick, this becomes, we got 2 to the k plus 1 plus 1. So this becomes 2k plus 2 plus 1. So 2k, this whole thing right here becomes 2k plus 3. So we're taking the limit as k is approaching infinity. I'm going to get a 7 to the k plus 1 over 7 to the k. I've got a negative 3 to the 2k plus 1 over negative 3 to the 2k plus 3. And I've got a k and a k plus 1. Okay, so that is how everything's going to group up, and lots of things are going to reduce. K plus 1 and k, we're going to get a 7 to the first power in the numerator. So we get 7. We could also, well, there's this term here we can't drop the absolute value on. So we'll leave everything in absolute value. So we got 7 on the top, 7 over 1. And here we end up with 1 over, we get negative 3 to the second power because there are, when we take the difference here, we would get negative 3 to the negative 2, and then drop that down. And then this k, we still have that k. I'm going to leave that there. We still have that k over k plus 1. But when we take the limit, that's going to pan out. So this right here becomes a constant. It becomes 7 over 9 times k over k plus 1. But it's a positive 9. This is in absolute value, but we can actually drop the absolute value. And the 7/9 can come outside the limit. So I've got 7/9 times the limit as k is approaching infinity of just k over k plus 1. Those are also both positive terms right there. The numerator and the denominator are both positive, so we could drop the absolute value. Of course, this is easy to see in a variety of different ways that that's going to approach 1, lead ratio of the lead coefficients, or we could multiply by 1 over k. So we get 7/9 times the limit as k is approaching infinity of 1 over 1 plus 1 over k, which this whole thing is going to approach 1. And we end up with 7/9 times 1, which is 7/9, which how does that relate to 1 for the ratio test? That is less than 1 for the ratio test. And so that means that we have absolute convergence. And so therefore the series from k equals 1 to infinity of 7 to the k over k to the first times negative 3 to the 2k plus 1 converges absolutely by the ratio test. And there we go. All right, I wanted to end this video just talking about rearrangements because we've been talking about the types of convergence, absolute versus conditional convergence. And so it brings up this question, like what if we change the order of a finite sum? So what if we had convergence, but we changed up the order in which we were adding the terms? So here would be an example when I say that. So if we have a series, let's say a sub n, and it's convergent, and we add up the terms normally, we would go by the order of the index, A1 plus A2 plus A3. Well, what if we just switched it up? What if we started by taking A10 and then we added A1? And then we added A20, so going up by 10s there to 20, and then A2, and then A30, and A3. What if we added in that pattern? What would happen? Would it have the same exact sum? Would it converge to the same value? So if we have a convergent series, if we rearrange the terms, we mix them all up, we shuffle them around, will it converge to the same value? Because when we think about adding a finite number of numbers, it doesn't matter. We can rearrange them any way we want. They will always add to the same value. But what about these infinite sums? Well, here's the thing. It actually depends. So here are two facts that you can put in the back of your brain, kind of as interesting facts about converging series. If a series is absolutely convergent, that strongest type of convergence, and it converges to a sum, we call it S, then A sub n, the summation of all the terms A sub n, will always equal S no matter what the rearrangement is. We can rearrange all we want and we will still converge to that same sum. So our absolutely convergent series behave as you would think a sum would behave. But what about those conditionally convergent? So remember that a conditionally convergent series is convergent, but when you take the absolute value, if you actually take away any sort of switches or sign changes, when you take the absolute value of the series, it is divergent. So remember that. So this is a weaker type of convergence. And if R is any real number, so any real number, then there exists a rearrangement of the series that will have a sum that will be equal to R, which is just sort of mind-blowing if you think about it, right? Like you've got a conditionally convergent series, and basically what we're saying is you can come up with a rearrangement that can be equal to any real number because we have this weaker type of convergence and we can push the terms around, tweak the terms, rearrange in any way that we want, and it will actually change what the sum is, what we are adding the sum to. So anyway, just kind of an interesting end to this section about rearrangements, but those absolutely convergent series will converge always, no matter what the rearrangement is, to the same sum.